Hi everyone, welcome back to another episode of Design and Application of Lasers. I'm instructor Dr. TJ Hammond. Today we'll be continuing and finishing up Chapter 5, Laser Oscillation, Power and Frequency. So we've talked on Monday, sections 5.1 to 5.3, using the uniform field approximation. We use this uniform field approximation such that the intensity going to the right and the intensity going to the left, or the field going to the right and the field going to the left inside of a laser cavity are approximately the same. We said that this is the case if there's not too much gain caused by the gain medium, and we don't have too much losses caused by the mirrors. From this, we could optimize the output coupling and show that when the losses equals the output coupling transmission coefficient, we get the optimum output power. On Wednesday, we looked at sections 5.9 to 5.11, which is discussing frequency pulling, how to get a single mode oscillation, how to move that mode around, and what the line width of a cavity is. For today's lecture, we're going to be discussing the Fabry-Perot etalon and the laser at threshold. So both of these are questions that are on your cumulative assignment 1. And so for those of you who follow along very closely to the notes and follow the textbook, these questions should be fairly straightforward. But because we will be discussing them here, I expect you to go through these derivations extremely carefully and understand what all the definitions are, and notice the questions that I ask won't be exactly answered here, so you can't just copy everything verbatim. The daily assignment that's due on the Monday after reading week is going to be 2 parts, so it's actually worth 2 marks. So I want you to think about what we've done this past week. Why do lasers emit in discrete modes? So we've talked about this week. How can we tune these modes? What can we do? Can we add to the cavity to tune these modes, or how can we change these modes or these frequencies within the cavity? How do we make sure we only have one frequency from the laser? Why can't we have multiple ones? And then also, I want you to think about what we've been covering this past week, and I want you to think about what you do understand, what you don't understand, and list any sections that we'd like to cover in further detail, or it's also fine if you don't want to cover anything in further detail. But I'd like to know what are problems for you guys, or what I didn't explain very well for when I teach this course again, in the future. And as I said, this is due the Monday after we get back. Okay, so what we'll be covering today is the Fabry-Perot etalon. So I'll be going through this derivation in class, but what you have is, what an etalon is some relatively thin optic with some index of refraction that will give N2, and it's in some, sea of material that has an index of refraction N1. Typically, this will be like a piece of glass, so N2 will be about 1.5, which is the index of about the index of refraction of glass in the visible, and N1 will be 1 because this will be, say, air, so it's like 1.0003 or something like that. So we'll just assume that's 1. So what you can have is, if this is just a piece of glass, then R1, the reflection coefficient of this glass, is going to be something like 4%. And then again, you'll have this back reflection here. The back reflection coefficient will be again about 4%. And you get a stream of photons coming in and hitting this glass. And I'll show you that we can go through this derivation, but the problem with this derivation is we don't take something very important into account, and that is the phase. And so that's what we always have a problem with intensity, is that we never know what the phase is if the thing that we see from an electromagnetic wave, we always see the intensity, we don't see the field. And so we lose that phase information. So we'll go through this derivation and show that although it would be right if we had a phase-free object, if these photons didn't have phase, it turns out that they do have phase, and so we should actually describe this in terms of the field. And so the field, remember, is a wave. It's an electromagnetic wave. And so we should actually be modeling with this phase where we have the phase that's a function of position, z. Where, of course, because this index of refraction for this glass, say, will be higher than it is for the air outside, then this wavelength will be shorter. So we'll go through this derivation, show what happens to the phase, and we'll see what the transmission and reflection of this etalon is at certain phases and things like that. But that'll be your question that you'll be needing to do, or that would be one of your questions if you so choose for the assignment. So I won't go through this derivation in great detail, and in fact my derivation will be slightly different from what the question asks, but it'll give you a head start on how to do this problem. The other thing that we're going to cover is laser at threshold. That's when we just get this laser to work. So we've talked about what the steady state is of a laser, and what the threshold gain is, and what the steady state photon rate equation is, and things like that. Now we want to kind of combine all these ideas together to actually discuss what the intensity is inside a laser cavity when we're near threshold. And so this will kind of give us a good clue of what threshold means. So threshold, of course, means just when we're at the threshold of this laser starting to work, just when it's at the threshold for being a laser. But we want to actually kind of quantify what this is. So I'll be going through the derivation in class. We'll be using this photon rate equation. The textbook makes some variations on this, and so we'll discuss those as well. But what you get out is this plot here that is reproducing figure 5.22, which is also a question from the cumulative assignment. But he makes a lot of substitutions, he makes a lot of approximations. And so I want you, if you're going to answer this question, I want you to carefully make sure you know what all those assumptions are, what all those approximations are, what all those defined variables mean, because that is, you're going to be walking me through how he got to this answer. The textbook skips a lot of steps and refers to other sections in the textbook, some sections that we haven't even covered in great detail. So you will have to be reading up on that. But the upshot is that if we look at the photon number inside of a cavity as a function of gain, that if we're at this gain right as a function of threshold, then right when we're at the threshold gain, you see that there's this massive increase in the photon number. So as we're increasing the small signal gain as a function of the threshold gain. So if you remember, the threshold gain is going to be dependent on the cavity losses, where the small signal gain is going to be depending on our pumping and our spontaneous decay. So as we're pumping harder and harder and harder, just as we reach this threshold gain, you see the number of photons just jumps by many, many orders of magnitude, something like 6 or 7 orders of magnitude in a tiny change of the pump power. And this is what it means to be at threshold, that you don't have this, you don't really get any photons out. This is just going to be very few photons, to all of a sudden you get billions of photons out. And that's what happens when a laser is at threshold. So this comes back to what we had talked previously, which is when we were talking about getting a single mode. So although we have gain for all these modes, you could think, well, we'll have this mode, but it'll be weaker, and we'll have this mode that's slightly stronger, this mode will be slightly stronger, this mode will be slightly stronger, this mode will be the strongest, and then this one will be weaker and weaker and weaker. And you think, okay, we'll get a series of these modes. And so, but I insisted on in Wednesday's lecture to say, no, what will actually happen is it'll laze at this mode, and then maybe hop to this mode, and then back to this mode. And you only really have one mode at a time. And the reason for that is just as our gain is reaching this threshold gain, that's exactly what's happening, is that we're basically populating one of these modes. And so this mode that's populated, say we're here, we get this many photons in that mode. So we get a huge number of photons in that mode, and so we get a huge amount of stimulated emission, and we get a really, really bright, intense laser beam. And that's why only one mode will laze at a time, is because all the photons will be here, and all those other modes, as we said, will be below threshold. And so all those other modes will only be getting hundreds or tens of photons in those other modes, whereas these ones have billions or tens of billions, for example. And so that's why we'll get only a single mode, because it's a single mode in, a part in 10 to the 10 or something like that. Okay, and that will wrap up our section 5, or our chapter 5, talking about getting power and out of a laser cavity and determining the frequency.